Yes, so today we'll be talking about like real-time analytics with Pino. So I am an engineer at StarTree. Mostly I've been working on like the upserts and the query engine part of the Pino. And before that, I've been like contributing to Pino since like 2020 or 2021. And like writing the JDBC driver, S3 support, and other like Kinesis support and other stuff like that. Yeah. So what is like, first let's focus on like what is the use case of Apache Pinot. So Apache Pinot is like real-time, low latency analytical database. So what do I mean by that? Like first of all, like it's an OLAP database. It's not an OLTP database. So a use case for OLAP database is something like you want to aggregate like last 6 months of booking data in an e-commerce app, or like you want to analyze the clusters of users who are doing your booking in like last week or something. While OLTP is something like you want to check the status of the booking of some user ID, A or B. So Pinot is meant to do like heavy queries on a large like span of data. While low latency, I mean is that like general expectation of OLAP databases is that you run a heavy query and you'll get results in like 1 second, 2 seconds, or even it can take up to a minute. Because generally OLAP databases have to transfer a lot of data from S3 or sources like that. And like that presents a lot of overhead. What Pinot excels is in that like it can provide you the latencies at the query time of the OLTP databases while being OLAP. And the second is the real-time aspect of it. So we allow users to query data like which is coming via the streams, not just which is stored in the S3. So if you have data systems like Kafka, Kinesis, Pulsar, you can simply like plug it into Pinot, and like within milliseconds of publishing some data, it will be available for querying. We don't do any batching or anything. As soon as we read the record, it's available for querying to the end user. And like that's what makes Pinot like unique in its offering. Yep. So initially Pinot was developed at LinkedIn. So the primary use case like was you see your, whenever you go to the LinkedIn profile page, you see who's viewed my profile section. And there are like a lot of other stats that are present on LinkedIn, especially for the recruiters. So you want something that can calculate all these stats when the user is querying them, rather than like having some pre-aggregated data, which is old, like was computed like 1 day before and is like cached somewhere. So this is where like Pinot was basically designed to do. LinkedIn has like hundreds of millions of users that can make real-time analytics query. So, and like this can only be done like with a system like Pinot, which can give you the results in milliseconds. Other use cases can be like, for example, you have like Grofers or you have like Uber Eats, where you want to show a restaurant manager like how many bookings have been done, like how many orders have been placed, where in which areas are our drivers located like right now. So all of this, rather than depending on the OLTP databases, you can simply plug in Pinot and like get all of those results like as quick as possible. So Pinot like currently is being used by like a lot of companies. We have like around 4,500 stars on GitHub. Like we have like a lot of Slack users. Our OSS community is really active. You can any day like ping to share your like grievances or anything, or if you want to chat about anything on Pinot, like you can just ping on us our open source Slack, and like you will get any one of the core members in like within minutes to answer your queries. So I'll touch briefly on the architecture of the Pinot. So Pinot, like the main design principle of Pinot is separation of responsibilities. So we have like multiple components. The major one being the controller, broker, and the servers. So servers are the component where you have to store all of your data, whatever like data is being consumed, and whatever you want to make it available for querying is present in the servers. And servers are the one that handle the query of a table partition rather than the whole table. And all of that data is stored, the Pino stores all of that data in the immutable tar files called segments. So servers are like horizontally as well as vertically scalable. So based on your like the data needs, and like they are the most heavily used component of the Pino cluster. Then like there comes the controller. So the controller serves as the like basically coordinator of the whole cluster. Each and every component of Pino knows only about itself. It has no information of what the other components are doing. Only controller knows what task should be assigned to each server, broker, or anything else. What do I mean by task? For example, you want to start ingestion from Kafka for some table. So which of these servers should actually ingest the data? That will be decided by the controller. And in case you want to scale up your servers, so from 3 to 5. So how do we know like which data should go to the new servers and which should remain in the old? So that is again like done by the controller. And how does controller gain that information? It's via Zookeeper. So all of the components in the Pino like update their state to the Zookeeper, and controller uses Helix to basically keep track of everything, every state of every machine in the cluster. And like on basis of that, like it takes the decision on how to assign the data and like do like basically ensure that your data is always available. The broker is where like your user, whenever user fires a query, it goes to the broker. Broker is like really simple. What it does is that you have a SQL query. It will simply transfer that SQL query into a tree which is understandable by Pino. And like it will then send that query to the appropriate servers. So, and those servers will like actually run that query because they have the data to run that query, and like they will return results back to the broker. The broker will aggregate all those results and like it will return them back to the user. So Minion is like was a new component that we only recently introduced. So the thing was like there are a lot of ad hoc tasks which happen in Pino servers. Some of that task could be like basically merging some old segments together because you don't want duplicate data like across the servers, or you don't want like a lot of files like basically polluting your directories and stuff like that. So what we did was like all of these tasks usually ran like on the basis of cron or something, and it basically like didn't allow us to, we were basically limited by the number of servers to run these tasks. So if you had 3 servers, but you had a cron job which triggered on like once per weekend. So you were limited by just those 3 servers to complete the task of that cron, which can result in like that cron job running on for like hours or even days. So what we did instead was like we again separated out that completely in the form of minions. And in the minions, we have this auto scaling feature. So you can like keep minion at 1 or 2. And like whenever that cron job runs, only minions scale at that time. Your cron is completed and like the minions scale down again. The deep store is just the like the S3 or any other distributed file system. So there in the default implementation of Pino, we just keep the segments at the backup. The data is served by the servers only because to ensure the fast latencies. But the segments are always available in the deep store so that you can basically easily transfer them across servers, and like to ensure that there is never a data loss in a Pino cluster even if a server goes down. So there are like a lot of differentiators in Pino compared to the other OLAP databases. The first one being the number of indexes we support. So we don't have just simple inverted indexes, which are like, for example, you fire a query, select all from booking table where user ID is equal to ABC. So that is on user ID, generally people create an index and like they expect that you can easily figure out like where does the user ABC lie in the data and like you quickly return the results. But we support a lot more indexes on top of it. Yeah. So we have like support for range indexes as well. So in the range index, you can do queries like where timestamp A is greater than equal to T1 and less than equal to T2. We have JSON index where we allow users to simply, rather than even breaking down JSON into multiple table columns, you can directly ingest the raw JSON itself in the Pinot. And even with that, like you will be able to query the individual key and value of that JSON at the same latencies as you would like if you had like broken that JSON down into multiple tables and columns. Like that presents an ease of access to the user so that they don't have to bother with creating like whole schema to ingest some data. Then we have like text indexes, which is like something like Elasticsearch offers. So in the text indexes, we basically allow users to search where string is like ABC and similar queries. And then we have like aggregation optimization. So the aggregation optimizations I'll cover in the next slide. The geo index is basically for the use cases like Uber, where you have to track which cab is at which location. So you actually need some way to quickly like get the count of like cabs at location, which can be identified by some polygon of coordinates. So we support like, I think H3, which is Uber's implementation. And so you can easily query how many cabs are located in a particular H3 cell. Yeah. Then we have like approximate like count operations so that users don't have to. Doing an exact count, especially the count distinct, is sometimes extremely heavy. So we support like approximate versions of those. So you can get 99.99 percentile results while like without like waiting for all the data to come together for a particularly indistinct operations to proceed. The next thing we offer is the StarTree Index. So StarTree Index is like you want to perform some heavy aggregation queries always on Pinot. Like select some clicks from table where country is US and browser is Chrome. Now you can do two things. Either you can wait for Pinot to complete that query. And to complete that query, it will have to basically search for all the rows using inverted index where that data lies and then do the summation of all these rows. Or you can simply create a StarTree Index. What StarTree Index does is that like it allows, it's basically a form of pre-aggregation during the ingestion time itself. So when you are ingesting the data, you can mention, I will perform the query where I will gather the sum of this column. And the dimensions I want is country and browser. So it will create a sort of a tree structure and it will pre-aggregate some of the data for which it knows like it won't see something new. And like there will be some amount of data which will not be pre-aggregated. So when this query actually runs, what happens is that like we simply fetch the pre-aggregated data from the index, and whatever we don't have available, we simply aggregate it at like the real time and like return the correct results to the user. So this allows like this makes the aggregation queries insanely fast because you have reduced the like the CPU time thing to basically do the aggregation to just a simple lookup. Yeah, so StarTree Index basically is just like, if you think in simplest terms, it's just like you can basically index like each and everything and basically depend on the index to do aggregation in the real time. Or you can pre-aggregate each and everything, which will increase your space to create that index. So StarTree Index just lies in between these two. And you can easily configure the StarTree Index to determine like how much like data do you want to be pre-aggregated to save up on space, and at the same time like providing the appropriate like latency benefits. The next thing we offer is the upserts. So upserts are like basically in the OLAP databases, like most don't support upserts because by nature the OLAP data is immutable. So in Pinot also, we have the same implementation. The data is fundamentally immutable in nature. But we still support upserts via like a metadata. Basically, we keep the metadata of where the particular like where is the latest data located for a particular primary key. And like the upserts like are supported like on real-time tables. So as if you have data coming in via Kafka, so for example, you have some order stream coming for each where you have some user and what is the status of that user in e-commerce site, if he has clicked add to cart, if he has actually ordered something, if he's on search base. So you can simply keep track of everything via the upsert, and like upsert will always return you the latest result, like what is the state of this user, and like you don't have to basically do all this during the query time. Otherwise, you'll have to write a whole long OLAP query to basically dedupe the data and like get the latest state. But Pinot does that by default during the ingestion. The next is the join support. So the joins, like we support two types of joins. One is the lookup join. So in the lookup join, what we do is that like we allow users to create dimension tables. And these dimension tables are located in the same servers where your data is located, so that you don't have to do any like cross-server communication during the join queries. It saves us a lot of latency at the like cost of like extra space. And like the next thing we offer is the full SQL join. Next. Yeah. So the full SQL join is like when this was only recently introduced, and like we allow like basically all servers to communicate to each other. And like if you want to join table A from table B, and like the servers communicate with each other, shuffle the data together, and like it will return you the final results. Like earlier in the earlier implementations of Pinot, we didn't allow servers to communicate to each other. They were like independent component. But now with this full SQL implementation, the servers also like are able to shuffle data between them. Yeah. Next. Cool. Yeah, so you can try out Pinot at like pinot.apache.org. We also offer free trial of StarTree. You can go visit our website to try that. And you can always join us like where each of our members is like active, and like you receive response within minutes. Yeah. Thank you.
Yeah, so good morning all. I'm Vaibhav. I work for Cisco as a part of the Webex group. Basically what I'm going to talk today is our journey of using Apache Pinot right from the inception stage, how we went about evaluating Pinot, and when we really got committed to Pinot, what are the open source contributions that we've been making across our team into Pinot. Okay, so this is what we are going to talk about today, which is the real-time observability using Apache Pinot and Grafana. And I know, I mean, seeing Grafana up there must be raising a lot of questions how we are doing Grafana, so I'll cover that in a bit. Okay, so before we dwell into the niceties, right, a bit about our team. So I work on the data and the analytics platform team for Webex, and so I'm sure at some point of your professional journeys, everyone would have used Webex at some point in time to have online meetings, right? So this is what is working behind the scenes. So Webex, just to improve your experience with the online meetings, we actually are continuously monitoring a lot of media matrices, whether you guys are actually having issues or jitters and all those things. And all of that data is actually flowing into the data analytics platform. And so just why we are a big data platform, everyone would be aware of the 5 V's, right, of the big data, so which is variety, velocity, volume, and veracity. So that is what actually fits in. So we have a variety of data, which is right from system stats to your media stats to basically what programs you're running in terms of CPUs, etc. So typically we handle around 100 terabytes of data per day. And at peak load, we could even get around 300 messages per second. So that is the peak load that the platform handles. Now, what really happened during the pandemic was all the online systems and the video conferencing systems, they were under load, right? And what it essentially means was everyone, everyone went online, everyone was having online meetings. And the questions that admins and our internal analytics analysts were asking completely changed. So there were jitters, all the customer admins wanted to know what was going on in their system. Suddenly they were bothered about what upgrade you've pushed, whether my jitters is because of the version upgrade that I've done, is it about too much of load on my network? So suddenly the number of dimensions on which customer admins wanted to do their analytics changed. And that actually posed a problem for internal SRE teams as well, because they wanted all these analytics available to them also, themselves as well, to actually answer the customer queries and all the things that were happening. And that is where we actually suddenly saw a rapid increase in the QPS of the systems. And obviously, since these were some of these features were customer facing, we required second latency and freshness of data. So imagine an event is going on, right? Your CEO is addressing a huge gathering, and suddenly you are like, I'm not able to hear him. What is the reason? The teams have to go ahead and fix that on the fly. So that is something that we were looking at with the changing landscape. Okay, so I mean, the classic thing always is, and I think, I mean, most of us have been faced with this question is, right, whether you want to pre-aggregate or you don't want to pre-aggregate. And pre-aggregate actually seems to be one of the easiest ways to go. And how I actually classify this is, I mean, I'm a huge matrix fan. So, I mean, any decision that I take, I always kind of refer to the blue pill and the red pill analogy. So do you want the truth or do you want to live in the oblivion, right? So we actually picked the red pill, and we decided that we'll not go the pre-aggregate routes. We'll kind of go ahead and explore the things, whether we can do it in a OLAP database. And that is where we actually started our evaluation journey of Pinot. So just the test bed that we were using was the telemetry data, which is around 1 billion plus events a day. So the test bed had 30 days worth of data. It has 150 plus dimensions just for the test bed, but just to put things in perspective, we have more than 650 dimensions that are in play right now in production. This were already stored in Elasticsearch, and Elasticsearch was good enough for us before COVID, when you did not have that much of dimensional analysis that had to be performed on the systems. And what we were doing, I mean, which is possibly anyone who's maintaining Elasticsearch would be doing, is rolling them up into a warm storage, basically move them from HDD-based storage to HDD-based storage to save cost. So this is something that we were doing before all of this was happening. And then obviously the big questions, right? And we started actually saying we'll not do pre-aggregates, we'll do runtime aggregates and look for a OLAP store. So this was our benchmarking process. So all the queries that we wanted to benchmark. So we picked up query patterns. I mean, obviously it's impossible to run every queries for benchmarking. So we actually picked up the query patterns that were most prevalent for answering such questions. So which was filter group by percentile queries. I mean, percentile is a huge thing, right? When you're talking about UDP packets, you really don't care about the exactness of the data, but you're talking about whether you are good enough. So approximations are good enough there. And obviously distinct counts. So this is what our results were. And we actually tested these results on concurrency. And we figured out, I mean, Pinot, so I won't read the results through, but what we figured out was concurrency versus latency. Pinot was a low linear growth, and Elasticsearch was actually an exponential growth. And if you see, most of my things on the Elastic side are TO or NA, which is either they timed out and we were not able to run through a higher concurrency because the previous test results were not good enough. So these were some of the benchmarks. And actually, if you look at it, there's a benchmark for the distinct count where even Pinot was going to 10 seconds of querying. But what Kartik actually mentioned in his presentation, the hyperlog. So if we actually shift to hyperlog, this goes into sub-seconds. And I mean, instead of distinct count, you just do with the 99% accuracy there. Yeah, so this is just on a parallelism of 5, it's just drawing a comparison between Elasticsearch and Apache Pinot. So if you can see across all categories, right? Apache Pinot was doing good for us in terms of the runtime aggregates that we wanted. And that is where we actually started investing heavily into Apache Pinot. The other criteria that we observed, so this was just by the way kind of an observation. I mean, it was not something that was in our measuring criteria, was the storage. And which is what we saw is what we saw in our test results was there was at least a 10 times reduction in storage space. And yeah, I was talking to some of the folks just before this meeting that why this happened. And it's just a theory. I mean, I cannot be quoted or held accountable for this theory, but the theory there is, if you look at how Elasticsearch stores its documents, is more towards JSONs, right? All your columns are JSONs there. And when you talk about metric data, it's numeric, generally 4 bytes. You know, you won't be able to have that much of compression in place. But Elastic, the column names are stored with each leucine file. So a lot of space is actually taken by the name of the field itself than the data that you are actually interested in. And that is what actually, I mean, and I think so, some of the StarTree folks should confirm this theory, whether that is what is happening here or not. Okay, so where we are in terms of our implementation right now of Pinot. So from the POC phase, we've grown to a sizable deployment cluster. So we run a cluster of 142 servers. So that is across our largest data center. I've given the specs. So each of the servers have 28 CPUs, 128 gigs of RAM, and 3 terabyte of hard disk. The total volume that we have unreplicated is 121 terabytes in the cluster. So with the replication, it would be around 360 odd terabytes that we have in the cluster right now. And from the Elasticsearch, we have a saving of around 500 instances, mainly because of the storage compression that we got by using Pinot. So that is around, we were down from around 800 terabytes to 121 terabytes of storage. Okay, so these were the good things, right? We've shifted everything. We've done your external or user-facing analytics is taken care of because that is generally through your apps. But as I said, the second problem that we have were internal SRE problems. And when you come to those, these are fairly technical users, but they actually are very used to a particular tool set. So the obvious question that comes is, how can I explore my data? I mean, Elasticsearch has a fantastic way in which you can explore data. And to be honest, I mean, Elasticsearch is pretty good in what it does. It may not be good at the matrix analysis, but it is really good at log analytics. So, and traditional, I mean, operational folks are used to that. They are used to Grafana, right? So, I mean, an obvious question here would be, why not use supersets, right? Superset has a really good visualization across the Pinot, and it has a great integration with Pinot. Why not use supersets? So we actually went ahead and told our folks to go ahead and start playing around with Superset. And they said, why are you making us basically learn a new tool? And with Superset, what happens to my alerting framework? I mean, Grafana has a good alerting, so why are you forcing what happens to my alerting? And Superset, how I put it, is more of a business analytics tool. You could compare it with something like Tableau, not really an observability tool in my opinion. Right, so what we started working on, and I'll jump into a quick demo for that. We actually started working on, so what we started working on in the background was how we could actually make the shift possible for even our operational engineers to use their old tool set that they were kind of very used to. And their old tool set was primarily around Kibana and Grafana. So we started actually building these two plugins. So for those who are actually aware of, Grafana can be extended to actually support your own data sources. So Grafana has this concept of plugins. So there are basically 4 plugins that Grafana supports. So we have developed the data source plugin and the app plugin for Grafana. So this is the data source plugin that we've built for Pinot. Again, this is not open source. This is ready for community review right now. We have not open sourced it as yet. So this is what we are doing. So it just takes the controller URL because, as you know, the brokers are actually discovered via the controller URL itself. So brokers are reachable, but all you have to do to configure the Grafana data source is the controller connections. Once you've actually gone ahead and configured the data source, this is how you can actually make a panel. So what we have is we have these support, which is time series, table support, and log support. Now, log support is right now not fully functional because this is something that we were exploring for CLP, whether we can use the decoders for CLP. So I know a recent connector came into Pino for CLP, so we were just exploring that. But yeah, so this is how pretty much it looks like. You pick up your data source like you would do for anything like Prometheus or Influx. You, let's say, pick up a table sort of a format. You select a query that. So I'm just going to pick up my table as what I'm using for, monitoring my Pinot query data. So I pick up, let's say, the total documents that have been scanned. Just for the interest of time, I don't want to go ahead and make a full-fledged dashboard right here. And I run the query. Okay, so I don't want to pick up a time series. I want to pick up a bar chart. So this is how you would go ahead and you can visualize on the Grafana dashboard. Now, this is one of the options that we are giving, which is a builder option, which is more of a UI tool. But to be honest, this does not do justice to what Pino can do for you, because something like regex, something like division operations, and all those things are not available through the builder option. So generally what we've seen, most of our platform users are actually using this code option. So you can actually go and write up any of your Pino query here. And this would actually help you go ahead and satisfy and basically go and plot your Grafana graphs. So this is the first plugin that we built, which was the data source plugin. The next plugin that we have is kind of the Kibana view. So as I said, our internal operators were very interested in how I can go ahead and explore my data. So this is like you would have picked up a Kibana index. You go just see which environment, which Pino table. This is the time, this thing, because that is required by Pino to construct a series, right? So some of the features that we have been doing in this plugin. So you see something like Hex here. I'll be talking more about our contribution. I mean, this is still a development phase because JSONs generally take a lot of storage space in any of the systems, right? So we are actually hexing it, and how we are hexing and still at the same time using the JSON index feature that Pino provides. So that is what we are using. So in this, you can actually see we have color-coded JSONs and all those things. And something which is very useful in Kibana, right? You can just go ahead and add a filter from here. So all that is supported right now in this plugin. And similarly, you could go ahead, pick up table names, or let me not do table names, query times. So something like what, a Kibana interface has, wherein you can add columns dynamically and even the time support. So this is a app plugin that we have done right now so that you can kind of give it to your basically operators to look at the data and to visualize the performance data that you want. So these were the two things that, two of the plugins that I actually wanted to demo that we are working on. Now coming to the open source contributions that we've been making in Cisco. So if you look at previous to this bounded column value partitioner, we already had a modular partitioner in Pino, which was, but the problem with the modular partitioner is two of your systems can actually go ahead and evaluate to the same modulo. You may have skewness of data there, and it's not predictable. So what we did was a bounded value column partitioner, which is nothing but it's kind of a enum-based partitioning that you may want to achieve. So it's a more predictable partitioning scheme. So this was a part of the .10 release of Pino. Then multiple column-based partitioning. This was actually a part of the .11 release of Pinot. So before this, Pinot used to just support partitioning on one column, and we had use cases where we had to do multiple column-based partitioning. The other where, I mean, you see a red dot there. So that is, so these two are already committed. The red dot in terms of partitioning is, we have not been able to kind of make it available for community review till now. So, but the backfill process enhancement that we've done. So traditionally, if you look at it, how backfills are done is, you do a backfill, you give it to your engineers to, or test engineers to go ahead and test whether the backfill has happened successfully or not. And then you actually, if it's not successful, you want to roll back, right? So this kind of a rollback feature was not, or rather is still not available in the open source Pinot version, because it is a straight off commit. So what we have done is we've kind of used the lineage feature that Pinot already has, and we have done some zookeeper enhancements here, so that you can actually achieve a rollback of the backfill that you want, or you do a commit and then you basically go ahead and discard the lineage that you have, so that it can be done in an atomic manner. Otherwise, your rollback would not be atomic, and you would see a bit of a downtime there. Now, on the visualization and alerting, I've demoed the two plugins that we have, which is the Grafana-based alerting feature and the Kibana plugin. On productivity, and this I'm sure most of you would have used this feature, is on the UI you have the user access feature that is there. So earlier to this, so this was I think so .9 or .10 version contribution. So earlier to this, what used to happen was you used to have users in your config files. You could not give dynamic user and dynamic permissioning to the Pinot files and to the Pinot users. So that was a feature that we contributed on open source. Now what we are actually even doing is all the Pinot connectors we are heavily contributing. So the Trino connector, we are actually doing a lot of bug fixes on the new gRPC support that Pinot has added. So our queries can be really faster here. And yeah, the next one is, I already talked about the hex support that we are doing. So we leverage the JSON indexing that Pinot has here. But at the same time, we optimize the storage by hex. So, I mean, we are able to achieve a kind of 90% compression by using the hex-based storage for JSON data. Key-based dedupe. So, if you look at, so we briefly before this talked about minions, right? So Kartik was talking about minion. Now, when you are actually moving from real-time to offline tables via minion, you can actually put the scheme as a dedupe scheme. Now, dedupe, it actually happens on all the rows of, all the columns of that row. Now, if you want to go ahead and do just a primary case dedupe, that is not available. So that is ready for community review, and we should be able to push that pretty soon into the open source Pinot. And next is the rollup enhancements. So right now, what the minion rollups actually does is it's single column based. Sometimes percentile is not supported. So we are making enhancements on our local port. We've already done that. But again, we have not integrated it with Minion right now. So that is why you see a red dot. We still are in the process of integrating that into, I mean, making it available for the community preview. Okay, thanks guys.
Thank you. So thanks Cisco and StarTree to invite us to speak at a conference and present our use case, what we did with Pinot. So I'll just walk you through. Can we go to the next slide? So we moved actually from Elasticsearch to Pinot for our users-facing analytics needs. So I have one more person from my team joining virtually. Unfortunately, he couldn't be here with us in person here. So I'm Shashank. I work as a director of engineering at the company, and my day-to-day basically is making sure that things are running smoothly. Development is being done, and I also contribute to a lot of code base in the team. So Rohit basically has been working with us as a data engineer, senior data engineer, and he has done a lot of good work on the Pinot side of things. So most of the Pinot-related things, he'll definitely go and talk about it. So we can just move to what Beaconstac is. So Beaconstac is a a phygital solution. Basically, we deal with a lot of QR code solutions. So what we do is we help companies track QR code analytics. So if assume like you are a consumer and you have deployed QR codes, you want to track metrics around it, who scanned it, where are the scans coming from, and analytics around it. Beaconstac is your tool for it. So we'll just move over to, yeah. So there's a couple of use cases that we have just presented here. So specifically about Pino, so we use Pino for our real-time analytics engine and just to serve all the queries that our customers do for their data in the system. So you can, so in terms of who uses us, so we have a lot of clients. So we have 30,000 plus customers, and from leading hotel chains in the US to Japanese OEM using Beaconstac to deliver information about their car models and at showrooms. We have a couple of big brands in multinational like food chains who are using us to run their menus or run campaigns on ads on their in stores or on billboards and a lot of other places or on TVs. So that's what the use case for Beaconstac is. Oh, so we'll just skip with the demo for now. Yeah. If we get time, we'll just show you the dashboard as well. So previously, we actually were using Elasticsearch. It's a very similar story to what Vaibhav actually, just showcased for Cisco. The only difference is, of course, Cisco is a very big organization that has a bunch of big amount of data. We being a startup, I'm going to give you some context about how we, as a startup, adopted Pino, like in terms of scale and in terms of usage. So very, very quick high-level design. So we have our, so whenever you scan a QR code, it goes through a lot of data like pipelines and comes to our analytics processing servers. From there, it moves to data streams to data enrichment lambdas that are running on top of it, and it gets delivered to, used to get delivered to Firehose, and then we have a backup that was being stored in S3, and the data was being pushed to Elasticsearch. And from the query side of things, so client APIs used to call the analytics servers, which are basically dedicated for fetching the analytics from Elasticsearch and presenting it in a visualization tool that the Beaconstac has. Okay, yeah. So I'm just going to talk about challenges. So specifically in taking Elasticsearch, we were running Elasticsearch for a while, and we were basically running into problems where we had to scale Elasticsearch again and again to every other 6 months we had to scale up the systems to twice the size to meet our needs. And we'll just talk about what the amount of data that we were running since we have the last we migrated to Pino was 20 nodes with a very vertical sailed system with 320 cores overall and almost a terabyte in memory. So that was the cluster size, and still with that cluster size, we are seeing huge latency on queries. So specifically, if you look at the, can we move to the next page? So if you look at the graphs here, so you can clearly see like the P95. Let's just forget about P99. P95 queries were around like 40 seconds or so. So these are like Elasticsearch queries that are being performed, and I'll just come to give you some other ideas on what exactly we were doing here as well. So we had a lot of timeouts that were going on with Elasticsearch, and very similar to Cisco's use case where there are either high latency or things were timing out eventually. Can we move to the next slide, Suraj? So effectively, this was affecting for our users itself. What used to happen, like people used to have to wait a lot of time to look at their analytics in the platform, and basically they used to get errors saying, hey, please retry fetching the data again and again, and this was causing a big problem for us from a standpoint of our usage and our customer base. So, and you can see the graph here. So you have like from some thousand errors to like 20,000 errors pile up on peak times on Elasticsearch. So yeah, can we move to the next slide? Yeah, so the other challenge with Elasticsearch being a very small engineering team, so we are a team of like 30 people or so. So we had a lot of challenges in making people learn Elasticsearch. So specifically when you go and try to hire people, for data engineering team, and you will not get a lot of people who are specifically well versed with Elasticsearch itself. So that was another a sub challenge that we had with growing the team itself. And I'll give you one more insight about the errors that you were seeing. So we had built in on the application side of things, we had built in retry mechanisms, which used to on Elasticsearch errors, used to retry things, and would try to get the data by just retrying things a couple of times. So that used to cause us in a callback helper saying, hey, I failed a 10-second query failed. It's going to run again for 10 seconds, which was causing a big problem from a scale standpoint. The QPS basically was very low on our Elasticsearch clusters. So effectively, we should have been able to serve around 100 plus QPS, but because of the high latencies and retry mechanism, we were in a situation we were serving around 30 or 40 QPS overall. So I'll hand it over to Rohit to present the solution, what we work with.
Yeah, so thanks a lot, Shashank. Yeah, so the issues with the V1 system that Shashank had discussed got us back to the drawing board. We realized that a long-term fix involves moving the backend to an OLAP data store. And we started exploring our options that were available. And that's when we came to know about Apache Pinot. And let me just move to the next slide. So we decided to do POC with Apache Pinot for two reasons. One is a really good documentation, which gets you started with a minimum deployment in no time, and a vibrant Slack community. You could post a query and you get help from someone from the community itself. So we created an in-house multi-node Pinot cluster and ingested 1 year of data for experimentation purposes. The first iteration had no explicit indexing, and even with that, we saw better runtime than the existing system. So this acted like a green signal for us. This acted like a green signal for us so that we could spend more time and resources on the POC. Then there were subsequent iterations with different combinations of indexing on the different columns, and it was done in consultation with the StarTree team. And we saw massive improvements in the query runtime. The current prod cluster uses inverted index, range index, and StarTree index on various columns. We also did a comprehensive stress testing on the Pinot cluster. Moving to the next slide. Yeah, V2 system. Yeah. Yeah, so this is the high-level architecture of the V2 system. The green box that you see on your left side remains the same. It has the V1 engine. We have the Beaconstac analytics server, which pushes the events to a Kinesis data stream. And there is a data enrichment lambda attached to it, which does some transformation and pushes the data to the downstream Kinesis data. And that it is ingested into. This is the real-time ingestion pipeline. We also have a legacy data ingestion. We have some legacy data. We use Apache Spark to process it and then write it out to S3. And then there is a minion file ingestion task, which ingests the data to the offline tables. This is a one-time ingestion task. Suraj, can you move to the next slide? Yeah. Low latencies. As you can see in this graph, the latencies of the various queries is between 0.5 and 1 second, and the P95 latency is less than 1 second, which is a massive improvement from the V1 system where the P95 was around 20 seconds latency comparison. So we saw 10x improvement in query performance, which translated to better end user experience. As you can see on the graph, the dark blue bars represents the Elasticsearch query runtime. For the 3 queries that we have on this graph, it took around between 10 to 15 seconds. And the light blue bar is the Apache Pinot with no indexing, and the query runtime has reduced to the max runtime is 6.3 seconds. And with indexing, it further reduced to less than a second. 0 errors. this graph is primarily the main reason for us to move to Pino. As you can see, we haven't encountered any query runtime errors. As I've discussed in the beginning, we did a comprehensive stress testing on the POC cluster, and we were able to achieve, we were able to support 100 concurrent users and 200 QPS with the median latency around 480 milliseconds.
Thanks, Rohit. So basically, from a cost standpoint, we saw like 50% reduction in number of nodes that we needed to run to serve the current user base and the growing user base that we have. And we actually downscaled the each nodes to use less amount of computation power as well. So we had like 10x reduction in the number of cores that we are running. So effectively, we were and 7x on the memory front as well. That's what we saved on by moving from Elasticsearch to Pino. For specifically our use case, there were Elasticsearch was not becoming as scalable for us. And specifically on the cores front, we are also like to point out the amount of cores that we are currently at and the node size, that number of nodes that we are running. We are able to run many more concurrent queries for Pino on Pino compared to what the same size of Elasticsearch clusters were running on. So yeah, that's basically from the cost reduction standpoint and the performance standpoint. So other benefits were observability became easier for us to, and we have like, of course, some managed solution over top of it, but observability became easier for us. The inception to Pino for new engineers and people that you're hiring, or the current people who start working on the analytics engine has become easier with SQL-like queries over top of on Pino compared to what we used to do on Elasticsearch. Yeah, can we? So basically, in summary, what we did was we saw like almost 90% cost in reduction on infra reduction and like 90% reduction in P99 latencies over top of by moving from Elasticsearch to Pino. And so we had, and apart from that, in the graph that you're seeing, actually there were no timeouts being shown there because they were not being captured at all. So we had like timeouts with queries running over 60 seconds for bigger amount of data as well. So there basically we had in the current systems we have 0 errors with the analytics engines. Thank you, everyone.
All right. Good afternoon, folks. I'm Atri. This is Rohit. We are from Uber, and we're going to talk about how we migrated from Elasticsearch to Pino for mobile app crashes. So I'll set some context around what the main problem was, and then Rohit will go into depth of how we executed this and what were the wins and learnings that we got out of the entire exercise. Without getting into too many details first, a very simplistic use case. So at Uber, we actively track our app crashes and bug reports. So people do tend to file a lot of bugs or issues that they see with our family of apps. And then we have crashes happening at on different platforms, different versions with different binaries, different app status. In some scenarios, we roll out a new feature and it suddenly starts leading to incremental crashes on areas that we might not have thought of. So we have an automated pipeline that tracks these crashes, puts them, collects investigated data such as stack traces and whatnot, and then puts them into a pipeline where some machine learning models run on top of it, and we can basically identify and tag certain crash types to roll out. So this kind of debugging or health analytics becomes much easier. So we have an internal code name for the such service, but we'll stick to that. So this historically has been on Elasticsearch because there were analytics performed there, and there was also a significant text search use case, as we can imagine. And recently, there was this effort as a part of the Elasticsearch deprecation program that is currently going on at Uber. We decided to move away from this stack and move to Pino. And one thing that we did want to do was not break feature parity and also get more wins out of it. So it should not be something that we're doing only from because we have to do it or from a mandate perspective, but we wanted to show real wins out of the Pino ecosystem. And we did get significant wins, as we'll see today. So yeah, that reinforced the fact that Pino is a great system at what it does. And many a times, people tend to misuse Elasticsearch for analytical capabilities.
where it should not be. And it's also a testament to the fact that Pino has come a long way in building new types of indexes such as text search that can augment its capabilities and allow people to do more than just simple time series. With that, I'll hand it over to Rohit to go into specific details, and then we'll take over questions.
So thanks, Atri. Yeah, just to add to what Atri was saying. So if you look at this dashboard, so starting from the first row, you see there are two graphs about total sessions and total users. So this is basically giving us total unique sessions and total unique users at the day level granularity. Similarly, the third one is showing how many total fatals or the crashes were there on a mobile app. So this is just a view of one mobile app for one operating system and one of the version and last 7 days of data. We then combine these metrics and then find fatal free rate, which is basically an indication of how healthy your application is. So in general, we try to have it as close to 100 as possible. If you see, there's a very small line which is under 99%, and then it gradually goes to 100%. That's mostly because we also have a cycle of beta app rollouts, wherein a beta app will have some experimental features, and then we want to track how healthy is it. And it only becomes eligible for a release for a wider audience once it has passed a certain threshold of fatal free rate. Yeah, and then there's an adoption rate graph. One line is going down, that's the older version phasing out. The other line is going up, that's the newer version coming up. And then finally, we also give how many, like, per crash module or per module of an application, which is the most crash causing one. So yeah, this is like a very snapshot view of it. We also provide in-depth crash level analysis. So each crash is also clustered together. So all the similar crashes will form a cluster, and that then we provide analytics around that cluster. So for example, let's say we launched a new feature on a particular screen, we started seeing a lot of crashes. So all those crashes for that particular screen are grouped together. Then there are a bunch of ecosystem services built around it. So for example, any new feature enabled via an experiment, as soon as we start seeing crash spikes for that, we'll directly assign it to the last person who made the code commit. And then there's whole ticketing and alerting system around it, and then people can work on it, and then it gets closed. So yeah, this was a very brief overview about it. Some similar enterprise solutions are like Bugsnag, Firebase, Sentry, etc. And we also do the similar kind of analytics for backend services log as well. So just like there are crashes in your mobile application, there can be backend service generating error logs. So we provide a bunch of analytics and clustering around them as well. So just to briefly talk about the numbers, so the session counts that I was showing, that is derived from the analytic events, and the scale of analytic events can go up to 200 or 300,000 per second. So you can imagine it's a lot of data we need to process if you want to store and provide unique session counts around it. Similarly, crash events can be double-digit number. It can be from a few thousand to 15 or 20,000 in cases if we are seeing some spikes in crashes. Payload size, again, varies a lot, few KBs to hundreds of KBs. And that's mostly because your crashes can have a lot of metadata around it. It can have network logs, analytic logs, and then any other crash payload around it. For example, the experiment payload, what all experiment parameters were activated during that time. And finally, the data footprint on Elasticsearch was around 150 to 160 terabytes. This is a very huge number just for the analytics purpose if you are trying to solve for. So to summarize, I'll say a lot of cost was from the ELK setup that we had. And it was not just the cost aspect of it. There were situations where if we have spikes in spikes in crash rates, then Elasticsearch would lag in terms of ingestion. So then we'll have larger ingestion lag. Because it's a larger ingestion lag, we'll be slow in identifying any issues happening. And given this tool has to be very near real time, this is a huge miss if Elasticsearch is not performing well. So this gave us the natural reason to move to something much better. And in our case, it was Pino. It's a very high-level summarized model. So if you see previously, the Kafka events are directly going to your ELK setup. It is now being replaced by a very simplistic structure because Pino has direct Kafka consumers, and it can directly consume from Kafka topics. There are some more changes needed. For example, your Elasticsearch can pretty much store any kind of structure of document. In Pino, it's slightly more schema-driven. So that is where we need some kind of transformation, wherein we use Flink jobs. There's also a branch which is missing over here. That's the offline data that we also push to Pino. And the offline data is being pushed because we are going to create hybrid tables over there, which will have the real time and the offline part. For visualization, we rely on Grafana and some of the internal tools. So that's how we were also able to get away from Kibana. Yeah. Looking at the existing cluster setup for Pinot, so we have an active setup. There are 2 regions. So this is the summary of one region. So we have around 6 real-time servers, 8 offline servers, and 2 brokers for querying. I hope the previous sessions gave you an idea of servers and brokers, but in case you have any questions, just let us know. So to summarize and comparing it with the ELK infra, so in ELK, we were using around 22,000 cores of CPU, but here we are doing it with just 2,000 cores of CPU. I'll go to the wins section wherein I'll give down the cost benefits that we have with Pinot. But this is just to highlight that how very less infra footprint can solve the same use cases which are being solved from Elasticsearch. And also to state that it's not a problem with Elasticsearch, but I think Elasticsearch has so many features at its disposal that we build so many things in very short amount of time. And then when it comes times for maintenance or scaling up, we just add more hardware to it, and that's what adds to the cost. In Pinot, we step back. We try to understand the use cases well before even putting any infrastructure numbers in place. Yeah, so let's look at the use cases being served by Pinot one by one. So yeah, this is the use case about counting unique sessions, users, devices at Uber scale. As mentioned before, it's like 300,000 analytic events coming at once. First challenge is consuming so many events in such a small amount of time. Either you need a very high scale throughput real-time processing system, or you, okay, if you solve that also, then you need some persistence which can store these many events in your storage. So what we did was we tried to understand the use case. The use case was to be near real-time. It wasn't to be super fine. So that means that we do not want point level analytics, but it can be fine if we provide some roll-ups in the metrics. So the approach that we followed is we rolled up the data at 10 minutes granularity for the real-time aspects. This was achieved by a Flink job. And Pinot's hyperlog column came into help very much over here. So hyperlog object, just to briefly explain, it's a probabilistic data structure which will allow you to do aggregations on unique count. So that's how we serve the real-time data. For the offline tables, we rolled up the data further with the hour and day level granularity. Again, so we have a Spark job setup which is doing the ingestion for the offline tables. So all in all, this helped us reduce storing so many events and then doing unique kind of aggregations across these events. We were having really good latency numbers. It was under 100 milliseconds for P99.5 queries. Yeah, so the setup was 45 days of retention, 3 days of data in real-time tables, and the 45 days of data in the offline table. Moving to the second use case, this was about counting crashes or analytics around crashes. So if you see, each row over here does not represent a single crash, but it's a cluster of all the crashes. Each title is the representative of a cluster of crashes. So there's a bunch of analytics around it. We show first seen, last seen, like first version where it occurred, how many users is it affecting, how many instances did we see in it, and how many devices does it affect. On the top, there are a few more summary numbers. So if you see, the queries in this nature, in this kind of use case, are mostly group by queries, wherein you are grouping by the cluster of crashes and then providing aggregation of metrics for each group. This was kind of an easy thing for Pinot because this is what Pinot is built for, and we also did not face any challenge over here. So again, this was a hybrid setup because 45 days of retention was needed. We went ahead with all the basic indexes. So this table has like around 10 to 15 indexes set up because of the attributes the data has. Again, this is an active setup to provide more reliability. For querying, we serve data from both the regions, but in case of any disaster, we can always roll back to one of the active regions. This also helped reduce the ingestion lag for us. So in ELK, we were, let's say in bad times when there was something bad happening in a mobile application and we see a crash spike, we used to see ingestion lag of few minutes, but now it's been under 10 seconds and crash spikes are handled much more reliably in this case now. And overall, it has improved the UX also. We have seen page load improvements from under 1 second to under 3 milliseconds. And the next use case was around providing analytics on the complex data type. So as mentioned before, these are crash payloads. They can have a lot of metadata around it. There are network logs, analytic logs, and these are mostly nested JSON data structures. So usually Uber is 1 or 2 versions behind the open source's latest version. So if you are, so at least from 0.12 version onwards, there's a lot of optimization in Pinot that has happened. So for example, you can define which path of a JSON do you want to index, you can exclude paths in it, and there are a bunch of improvements around how do you query a complex JSON object. But at the time of onboarding this use case in Pinot, in Uber, we were still at 0.11. So we had to go with the approach of exploding this complex data into key value pairs, and then we were able to easily support these use cases. The thing with exploding is that you increase your data events that needs to be ingested. But our experiments and also the theory of Pinot say that it's very good at handling scale of ingestion. And that's also what we see over here. Yeah, but in the long term, we have a plan to move towards JSON index and utilize all the optimizations improved in the 0.12 version. Yeah. Another aspect is, I mentioned that crash payloads can have variable sizes, and then these can be large and very small payloads. So one of the challenges which we were facing is that how do we tune between the segment size and segment count? So Pinot offers you the capability to either define a row flush threshold, that is, after how many number of rows do you want to seal your segments, or you can define a size as well, that is after how much time you want to seal your segments. And then finally, there's a timeout threshold. That means that, let's say, after every 1 day, we want to seal a segment. So in this scenario, we did not go with the memory or the size-based flushing, but we went with the row-based flushing. That's mostly to restrict the number of segments that we are creating and restrict the number of segment commits that happen. Because what happens in a spike situation is that you'll see a lot of data, and if you're doing memory-based sealing, then you start committing too many segments in a short span of time. And that adds to ingestion lag. And the thing that we don't want is during any disaster happening, we do not want any ingestion lag, just to quantify the right, just to quantify what is the extent to which the application is not performing well. So we experimented with large segment sizes. The final approach that we adopted was that we'll try to keep the segment sizes under 1 GB, and based on that, we were able to come up with a row flush size. And in many cases, we were also seeing that up to 3 GBs of data is very easily, 3 GB of segment sizes is very easily supported through Pinot. One optimization that we did was we primarily banked on the fact that we should be doing peer downloads for segments, for sealed segment, instead of relying on the deep store, because in our case, the deep store is HDFS, and pulling data from HDFS usually timed out for the largest segments. Yeah. And one more optimization that we did was we compressed our payloads. So it was the application side of compression, and in Pinot side, there's a support for byte column. So that's how we were able to support it, Pinot. Yeah. And the final aspect was around text indexes. So since these are crash payloads and there can be error messages or the stack traces, there was a requirement of doing a lot of text searches. So we leveraged Lucene text indexes, which are there in Pinot. So what it helps in is it provides you the standard analyzer, which will basically tokenize your stack traces based on dot separators. So you easily get class name or module name based on which you can do filtering. There's also support for phrase text, so phrase match. So let's say a service is producing logs with some custom message, so users can come and search for their messages. So we felt that there is a need for more analyzers to be added in the Lucene indexes, and we've also created we have also taken up the task for adding this to Pinot. I've attached the link for it, so you can follow it if you want to. And then there were some issues, there were some minor bugs that we also encountered, and this is mostly because these segment sizes were often reaching their max size limit. So for example, in one scenario, we were seeing that our segments were not sealing because the index size was becoming more than 2 GBs. In terms of implementation, what it meant was the offsets were of type integer, and they could not store a number greater than the integer's max limit. So we bumped up the forward index writer version to version 3, which is also already there in Pinot. And this provides us the offsets of long type. And now we were able to seal the segments in which the indexes could be of size more than 2 GBs. There was also a race condition that we encountered in which our segments reported that they were healthy, but they were not consuming anything from the upstream. The bug was mostly around that the Kafka consumer thread was not getting spawned. It was being created from the constructor, and Java does not get. So it was being created from the constructor, and so it's very interesting. You can follow this bug. The thing is that there are certain limitations you can do inside the Java's constructor, and that's what the bug is solved. Yeah. And in the long term, we also plan to move some of the use cases to native text indexes because at least in the mobile crashes, we see there's a lot of structured data. And with just minor massaging of the data, we can migrate all our use cases to native text indexes, which gives us very good cost benefits in terms of the amount of data stored and the amount and the time spent on querying the data. Yeah. To summarize our wins over here is, so we significantly reduced the mean time to detect whenever there was a disaster, because a disaster translates to spike in ingestion traffic, and spike in ingestion traffic was causing ingestion delays in Elasticsearch. And this is how Pino is outshining Elasticsearch over here. So it's easily able to handle any kind of spikes in coming from Kafka side. And that's mostly because it avoids writing to a file and keeps everything in memory. We were having significant infra cost savings. We reduced our CPU cost from 80% by 80%. Our ELK cost, the previous setup cost has reduced by 70%. Our data footprint has reduced to 66%. So currently we are storing around just 50 terabytes of data. There's been a significant improvement in the UX, and the end users have also given a very good feedback on the UI. So there's a significant lower time for page loads. And then finally, it's all about reliability, which matters for tools like these. So better tolerance to spike, quicker lag recovery. So even if we see any kind of ingestion lag, which will be in just magnitude of minutes, so we were able to recover quickly from there. We also reduced the query timeouts. We were also able to reduce it. So in Elasticsearch, the technique which was being followed was that we were creating weekly indexes. So let's imagine that there was some disaster in mobile application, and because of that, the index size increased. So whenever you do a query which is touching that particular index, Elasticsearch usually used to timeout. But in case of Pino segments, we are able to control the segment size instead of creating them based on time duration. So in this case, and then these are also better, like the queries are better scattered and gathered over here. So that's how we had reduced the query timeouts as well. And there's another important thing that we were able to fix is that there was a lot of data misses that used to happen whenever we had increased ingestion throughput in ELK. But in terms of Pino, we are seeing literally no data loss at this moment. Yeah. And in terms of learning, I think the biggest learning over here is we need to understand the use case very well before supporting. I think there should be a proper stakeholder, like we should manage the expectations between our stakeholders. So if you just go and look at the Pino documentation, you might find this like a fancy thing that can do all the things, but you really need to understand the use case. For example, we were able to remove use cases like requirement for upserts because we were able to do some deduplication in the processing pipeline. We were able to identify what are the tier 0 use cases and tier 1 use cases. And based on that, we provided storage tiering. So for example, the most recent data has to be queried highly, like more frequently. So that's why we did storage tiering over here. So our offline tables are served from high IO machines, and our real-time tables are served from high CPU machines. And again, over here, Pino has the configurability to use tag-based instance assignment in your tables. Second is that you cannot just let the use case owner team to write the queries. You also need to understand how they are writing the queries. And that's mostly to do with because people have in general relational background. So they try to solve things based on relational queries. But this is where we need to understand how we can like solve it in a manner that Pino actually supports. So for example, there were requirements of join queries, which we were able to solve with subqueries. Then again, there was optimization with ID sets. So people were putting in static list of data for doing in-clause kind of queries. And we were able to solve it with, again, subqueries, which had ID set kind of optimization. Third is you need to tune the segments really well. So I'll say in most of the cases, like 90% of the Pinot use cases, you might not need it. But when you have a high scale problem, then you really need to look at your segment sizes and the segment count. So when we had higher or the larger side segments, we were seeing timeouts from the deep store whenever table restarts used to happen and the deep store copy needed to be downloaded. And when we had too many segments, then it was usually because too many commits were happening, and that was causing ingestion lags. So these were the things we found, and I felt that tuning segments is also an important learning over here. And then finally, there were issues around data skewness. So if your Kafka stream is not partitioned properly, you will, if you look at Pino's architecture, you have partitions created per, segments created per partition of Kafka. So if your data distribution is not even across all the partitions of Kafka, you'll also notice the data that is being stored in the hosts of Pino, that will also be skewed. Problem with this is that some hosts can be overutilized very early and some will be underutilized. And you might run into a situation where you can have hosts going down. Second is so you can still have data distributed evenly across your machines, but internally data can be highly skewed during the query time. And it's because of some of the filters can lead to too many rows being scanned whenever you serve the queries. So in this case, what we did was we tried to focus on solving for the P99 and something which was which had to be solved. Like, for example, the recent data matters most in terms of logging on logging kind of services, which is this one. So we made sure that if we can solve it by giving more timeout for the older queries which are least frequently used, then also it's a good solution. So that is what we did. In some cases, we increased the timeout for the queries because they were infrequently being done. And in most of the cases, the queries did not time out. Yeah, I think, yeah, these were the learnings from our side. Ati, do you want to add something?
Thank you, Rohit. Yeah, I think that's pretty much it. Rohit's done a great job of covering all the aspects that we had. And one thing I do want to highlight is that this was, again, a critical service, and we had no outages during this migration. So that was something that was a factor of both Pino's reliability as well as our own preparedness in the overall migration. And yes, we have other use cases going on as well apart from this, which probably have a higher scale. And we have been seeing consistent improvement areas in terms of what Pino can do better, for example, with table rebalancing and upserts in general. So I think as the migration, I think I've seen more use cases here where people are moving from Elasticsearch to Pino. So this overall journey where people are moving from a full text search, which is kind of also analytical engine, to a true time series analytical system, I think Pino will definitely improve. There are many other areas of improvement that we probably would not, we as in the Pino community would not have thought of before. But with such use cases coming in, I think the evolution of Pino is guaranteed. So yeah, I think I'm personally very excited about this, both as somebody who's involved in the overall migration and also as a Pino community member. And we should be exchanging notes across this with other team members. So yeah, thank you, Rohit. I think that's it from our side. We would love to take any questions.